Okay, so as far as the mechanism goes, you guys are not going to test it exactly on it, but on the first step, you're definitely going to get a question or two, maybe. So remember, benzene, it's an aromatic compound, right? Aromatic compounds are really stable. We love them. Now, after we do the first nucleophilic attack, we're going to go from an aromatic molecule to a non-aromatic molecule. So we're losing that stability. So that's going to take a lot of energy to go through. That's why the first step is going to be your rate limiting step. Okay. So basically, it's just going to be the formation of your arenacium ion. And yes, you guys have to memorize that name as well. That's very important. You might get a conceptual question on this.
Is arenacium specific for bromine, or is it any
in general, for any of the reactions, yes. Again, the formation of the arenacium ion, that's your rate limiting step. That's it. That's all you have to know for the mechanism. And then at the very end, of course, we want to regain that aromaticity back. So that's where we're basically just substituting one of the hydrogens in benzene with whatever reagent we were given. And that's it. We're basically just adding something new to the molecule. That's it. That's the whole gist of the chapter. Okay, now. The spider web in here, that's summarizing all of the reactions that you're going to encounter for this chapter. It's just 5 of them. We have nitration, sulfonation, halogenation, alkylation, and acylation. And I would recommend to just memorize those names just in case. Because sometimes he's going to give you the name of the starting molecule. So it can be toluene, for example. And he's going to say that you're doing a nitration. You're going to have to know what kind of product you're going to get with a nitration. And you also have to memorize, of course, the reagents that are highlighted on the top. Okay. Everything is very important. Now, what you're going to see in common with all of the reactions is that they all have some sort of Lewis acid as your solvent. That's going to be the main part. Okay. You guys have to remember this. It's a Lewis acid. The solvent is always going to be a Lewis acid. You might get a conceptual question on this. Now, the only reactions that are going to be really, really special are the ones on the left side. The purple and the pink. I think it's red. Pink or red, whatever. But those reactions are going to be very special. They have special rules and they actually have a special name, which are going to be your Friedel-Crafts reaction. So those guys sometimes are not going to be able to happen. And that was the case whenever we had any strong electron withdrawing groups or any amines. Now, we know electron withdrawing and donated groups from chapter 15, right? Do you remember them? Okay, that's good. Now we're not going to be calling them quite like that. Our electron donating groups, now we're going to call them activators. And our electron withdrawing groups, now they're going to be deactivators. Okay, that's going to be the new terminology that we're going to be using. Now, your alkylation, the reaction in red, that one's going to be even more special because that's the only reaction that you're going to see that can do rearrangements. So that means hydride, methyl shift, those guys are coming back. Ring expansion, that's coming back as well. So if you feel a little iffy with those guys, please start reviewing them early on. They were from chapter 7, I think, in Orgo 1. You guys can look back at your notes. We don't have our notes. Chapter 8, one of those. Yeah, it was one of the later chapters. Okay, so far we're good. We starting to remember this from Friday? A little bit, okay. And in this case, I just posted a little, basically a review sheet for you guys for hydride, methyl, and ring expansions, especially for the ring expansion. That's the one that trips up most students. Okay, now, before we talk about our directors, every single benzene group that you see in there, you guys have to memorize how the name is going to be, the common name. So for example, for the first one, whenever you see a benzene group with a methyl group, we're going to be calling them toluene. Okay. And sometimes you're just going to be given the name of the molecule and the name of the reaction, and you're expected to find the product. Okay, so that's why you have to memorize them. They're not always going to be drawn out. Usually the common ones that you're going to see are toluene and aniline. Those guys are the most common ones. But again, any of those molecules, it's fair game. Yes.
It kind of was.
I don't know why it wasn't like him, but yeah, it shouldn't happen.
The exact same one that we went through.
In tutoring?
I think so. It was like
Yeah.
So 1, 3, 4, the bromine, and then the para.
Oh, yeah, it was with the positions, ortho, meta, and para. Nitrobenzene, that's just NO2. Nitrous NO2. Okay, so again, start doing flashcards. I don't know, start color coding. But again, it's very important that you guys remember every of those structures and their names. Before we go over that, let's talk about our directors. So we have two main types. We have activators and deactivators. What you have to know is that activators are always speeding up the reaction. They're making it happen a lot faster. So they're going to be your electron donating groups, okay, from chapter 13. Now your deactivators are the complete opposite. They're electron withdrawing groups and they're going to slow down the reaction, okay? You can pretty much figure it out by the name, like activator, it activates a reaction. Deactivator, it just slows down the reaction. And then, do we remember the positions? Ortho, meta, and para. Yes, ortho is 1, 2, 1, 3. Beautiful. Yes. And again, remember, you're always using those positions to a reference point. It's not always going to be at the very top. Sometimes it's going to be over here. But remember, you have to focus those positions in wherever your reference point is. So be careful with that. Okay. Now, on Friday, we briefly talked about this, but all of the molecules that you see in there, those are all the possible directors that you might encounter on the exam. Okay, and it's color-coded for your convenience. Everything that's blue on the left is going to be your activators. They're the ones who are going to speed up the reaction. And they're always going to be adding to ortho and para positions. Now, the very next one is when we start talking about deactivators. Now, for deactivators, we have two types. We have weak deactivators and we have strong deactivators. As long as you memorize the weak ones, you should be pretty good because the only weak ones are going to be your halogens, and that's it. But the tricky part is that your weak deactivators go ortho and para, just like an activator. But the strong deactivators, they're only going to go to the meta position. Okay. And that's pretty much it. And again, this is the memorizing portion. Yes. Halogens. Yeah. And if you want to know the specific order, I provided it for you guys. So fluorine is going to be more reactive than iodine, just in case you want to know. And then aldehydes are more reactive than ketones, for example. Okay. And you guys, yes. Yes. It was just to put in the range in case you guys were to ask me that. Because I do not remember this from memory. So there you go. Now, this list, you don't only have to memorize it like each of those molecules individually. You have to memorize them in that specific order because you're going to get some reactions thing where you're going to get multiple directors and you're going to have to see which one is the stronger activator, for example, or which one is the weaker deactivator. Okay, things like that. So again, please start early. Start early. It's a lot to memorize. It's really a lot. Either way, let's get back to our practice problem, which we're on page 4. And let's do a quick recap of the ones that we solved on Friday. Okay, so the very first one, we have a little benzene, and we see an alkyl halide, a carbon chain with some sort of halogen. So that's going to be our alkylation reaction. Now for this one, remember, that's the special one. That's the one that doesn't happen if you have any amines or strong electron withdrawing groups. In this case, we don't have anything on the benzene group, so the reaction is just going to proceed. Now, next thing about this reaction is that it can do rearrangement. So we know that the leaving group goes away and we're left with a carbocation. In this case, it's primary. So if we can make it better, we're going to do that. In this case, with a hydro shift, it's going to be secondary and that's more stable. So after you make your carbocation stable, that's when you can add it into your benzene group. And in this case, because that benzene doesn't have any directors at all, I can add that carbon chain anywhere I want. Okay. So far, questions on the first one. We're good? We remember it? Okay, now the next one. It looks very similar. In this case, we have a carbonyl group. Now, carbonyl groups can also be called your acyl groups. Acyl groups are just some sort of carbon chain connected to a carbonyl area, and that's it. So that's why the whole purple portion, that's your acyl group. Now, Similar process as we saw with the other one. We have a leaving group, so that's gonna go away. Now, whatever's left over, that's gonna get connected to the benzene group. And in this case, we do have some sort of directors. NH2. What kind of functional group is that? It's an amine. And this reaction is one of the picky ones. So it's not going to be able to happen. That's why this one is actually no reaction at all, just because we have that amine group. No, amines are activators. But the rule for the Friedel-Crafts reaction is that they're not going to happen with strong electron withdrawing groups or with amines, which are activators. Okay. It doesn't react with amines or strong deactivators. Okay, so far questions. So far we're good? Yes. Don't worry.
No reaction because it can't work with amines or strong deactivators.
Yes. Now on this one, we did something very similar. We see a carbon chain with a halogen, alkyl halide, alkylation. So we know that chlorine goes away. We're left with the carbocation, but it's primary. So we're going to try to make it better by doing a methyl shift. So now we get a very stable carbocation in the tertiary position. So now we can add it in the ring, but we're giving bromine in our benzene group. So that means that that's going to be your director. Bromine, is that an activator or deactivator? It's a deactivator, it's one of the weak ones. So that means that it's going to go to the ortho and pair positions. And again, this is my reference group. So that's why those two carbons are my ortho positions, and the one right across from it, that's your pair position. Yes. We're going to talk about that one. So hold on. This one is going both ortho and para. So technically we're going to have two products, but your professor is always going to be asking for the major one. Now, in this case, I just showed you the pair product because that's going to be the major one. But any guesses on why the pair product is going to be more stable than the ortho product? Exactly. There's less direct hindrance overall. So the molecule is going to be more stable. Remember, we always want to create something that's really, really stable. So far, questions on alkylation, acylation, how to use the rules and the directors. We're good? Okay, now. He should. Yeah, technically he did cover it like on Friday, right? Yes, he was mostly talking about those guys. Yeah, those guys are the most tricky ones because they have the special rules. The other ones, pretty simple. But we have 5 practice problems in here. So I'm going to give you guys 5 to 8 minutes to give me the major products in each one of them. And just take 5 to 8 minutes. You guys can look at your notes. The first reaction is going to be over here. This is 1, 2, 3, bless you, 4, and 5. I think it's a 5. This one? Yes. No, I added it. Sorry, I added it. Yeah. I forgot to put it in the actual handout, so that's on me. Is with the kind of reaction that we're doing. So acylation and alkylation, those guys are not going to react whenever you have any amines in the benzene group or any strong deactivators, like a carbonate. If it's present, yeah. Oh, yeah, that one is going to be no reaction at all. Simple as that. Exactly. That's it. We see a strong deactivator, the reaction is just simply not gonna happen.
Does the fact that there's a partial chlorine there affect like that
It should,
outcome at all? Or would, if there was another substrate, would it push the reaction and it would work?
No.
NO2 doesn't.
yes, with real cross reaction, it doesn't work at all.
Being strong deactivator makes it happen.
Exactly.
But also if it was NH2, it also.
It wouldn't happen, exactly. And then the other four reactions, they don't have any director, so they're gonna be able to proceed. But remember, some reactions might have rearrangements, so be careful with that. That was one of the rules.
Well, the initial step of the halogen adding on to the next, it doesn't matter where we're adding on,
In
right?
this case, no, because we don't have any director, so you can add it any.
So, on the- How are we gonna know which one is right? Is he gonna make it pretty obvious? Or is he gonna ask about the nature? How would you know?
He's always gonna ask for the major one, or he might ask for all the possible products.
Okay,
But as we move on through the chapter, I'm gonna tell you some formats of the classes on the exam.
so.
Either way, wherever you add it, at the end, we can rotate that molecule, and we're always gonna get the same exact one. So, yeah. Emily, did you have a question? Okay. check.
I guess I'm just like making sure, can I move this right here with the highlighter?
No.
No.
So rearrangements are only gonna happen with alkylations, not with acylations. And Sam, you had a question?
Ring expansion, carbocation is here, less torsional string within the ring.
But
Would
the
I do,
carb,
would I do another ring expansion?
not a ring expansion. You're on the right track. After we do a ring expansion, usually a hydro shift follows.
So another hydrogen shift here to cubic carbocation here.
Uh-huh, there you go.
So both methods.
We adding these groups in the reagent, or we adding just.
So remember, halogens are just gonna be your leaving groups. Whatever is left over, that's what you end up adding to your benzene group.
question?
Okay.
You know, like really mean, so it's a activator, but it's not super reactive. So then would this be a poly substitution? No?
No, so remember the directors, they have to be present in the benzene group.
Oh, sorry, and the start.
It's not whatever you see on the arrow. It's okay. It's okay. It's okay that you guys weren't happy with whatever grade you got. I know that you guys had high expectations, so it's okay. Just the second one. There's gonna be extra credit, so you have cushion. So try not to worry too much about it. You have the weekend to relax. So try not to think about that. Just chill.
Mild red, red.
Which one's that?
So like the bottom one. Sorry, so
Somewhat similar. You're missing one little bond. You are correct, but the benzene group is still a benzene group.
Oh.
Just remember, we're just substituting one of the
Oh,
hydrogens.
just lose the hydrogen.
Exactly. Where are we?
How about now? That's
Great
it.
job, Sam. Okay, do we want to do volunteers today?
Flex.
No. Okay. So let's go through the answers. So for this one, what kind of reaction are we doing? What's the name?
Alkylation.
It's an alkylation. So that's the special one. That's the one that can do rearrangement. So we know that bromine just goes away and we're left with the carbocation. Is that going to be the most stable carbocation? How can I make it better?
Slash, ring expansion.
Ring expansion, exactly.
That's actually a methyl shift. Isn't a ring expansion a form of a methyl shift?
In a way, yes, but it's an intermolecular one. So yeah,
But it's its own.
yes, it has its own name because the whole effect is with the ring, but either way. It's okay, you guys can say wherever you want. But what was the rule that you? So I mean, whatever your carbocation is right next to the ring, you do a ring expansion. If the ring has less than 6 carbons. Yes. Emily. No. We only do ring expansions whenever the ring has less than 6 carbons. So in this case, we have 5. Do we have 5? Sorry, we have 4. So we want to make it a little bit better. And ring expansions, they're only going to increase 1 more carbon, and that's it.
That was my next question. If the carbocations were on the rightmost methyl, would we do a hydride shift to get it on the secondary and then a ring expansion?
You can only do 1 rearrangement in that case. So you would only do the hydro shift to make it secondary. Actually, technically, you could do
No,
the
you
ring
could do a
expansion, yeah.
hydride shift to get it to that
Yeah.
allylic position maybe.
Yeah, you can. That's right.
I mean, because that's essentially what we're doing here with the hydride shift, getting it here so that.
Yeah, just 1 extra prior step. So yeah, that
So
can
that
happen
works.
too.
Okay.
Emily. Yes, the ring expansion is gonna make the carbocation more stable and the ring more stable. Because of ring strain, remember, any rings that have less than 6 members, there's a lot of ring strain.
And we don't want to push it to a 6-member ring because then it loses the tertiary carbocation position. Correct?
If possible, you're gonna create a 6 carbon ring. But in this case, that's only gonna be wherever you are starting with a ring that has 5 members. Remember, we only add 1 more. But do you guys want me to break down the ring expansion like step by step? Okay, let's do that. Let's do that. Okay, so that's a carbocation from the initial step. Now, after that, I'm just gonna start labeling my carbon so I keep track of everything. And usually I just like to start counting by the carbocation and then move on to the ring. But again, you can start wherever you want. This is not following IUPAC rules or anything like that. It's just to help you keep track of everything.
Okay, yeah, so that's why exactly.
It doesn't really matter, no. That's how my brain
As long as you,
prefers it.
like, visually see it.
Exactly. As long as you visually see it, you're pretty good. Now, the way in which ring expansions work is that usually your carbocation is going to be right next to the ring. It's going to be in the carbon adjacent to it. So we're basically just going to connect the carbocation to the ring. So to do that, I'm making a new bond, but I'm also breaking one of the bonds in the ring. So I can add that extra one. So I can open it up, basically. So far we're following. Okay, so far we're good. Now, after that, let's see what's going to happen. And let's do. Oops. Okay, now. So far, this is what just happened on the molecule, okay? It's drawn oddly so you guys can keep track of the bonds, and that's it. But I'm gonna redraw it into the actual way, which is gonna be your normal cyclopentane. Again, this is just for your benefit. If it confuses you, scratch it off. That's it. But this one is gonna look like this in practice.
Nice.
Whoops. Carbocation there first. Okay. It's not gonna stay on the 1 because that carbon now is gonna have 4 bonds. So it's gonna shift to carbon 2 because that's the one that lost 1 bond. At the end, yes, we're gonna do a hydrate shift. So that means that the little hydrogen here in carbon 1 is gonna move over there. So the carbocation can be even more stable. So now I have a ring that has less ring strain and a very stable carbocation. Okay, questions? Do you remember this from Orgo 1?
A little bit, yeah.
A little bit. Okay, that's good. Okay, so now that we have the most stable carbocation, now I'm just gonna add it into my benzene group. And in this case, because I don't have any directors, I can add it to whatever carbon I want. So it's just gonna be over here. This is the new bond, and then I'm gonna connect the actual molecule. Am I drawing this yet? There we go. Okay, so far questions on that one. Usually the only tricky questions are gonna be the ones with ring, because most people get confused with which bond is gonna go where and where the carbocation is gonna go. But usually it's gonna be very obvious. You just increase 1 extra carbon, and then the carbocation should always go to a tertiary position. So you don't have to go through the long process because it's not gonna be as tricky as Orgo 1. It's gonna be pretty simple, and usually it's the same ring expansion all of the time. But either way, let's go over here. We have benzene with that guy. What kind of reaction is that?
Solution acid.
It's an acylation. So remember, this is an acylation because we have the acyl group. Acyl groups are just the carbonyl area with some sort of carbon chain. That's it. So whenever we have acylations, we're just gonna cleave off that leaving group, and then whatever's left, we're just gonna attach it into our benzene group. And that's it.
Acyl group, ACYL.
Yes. This portion, that's your acyl group. So yeah, as you can see, there's a pattern in this chapter. We're just adding a little portion of the reagent. That's it. As long as you follow the rules, you're gonna be good. Yeah. But again, please be careful with the rules. Don't mix them up between the reactions. Memorize the directors. What kind of reaction is this? It's also an acylation. So same process. Chop off the leaving group, attach it into your benzene group.
Okay, so you don't do anything.
Wow.
It's a pretty easy chapter. You're just chopping off something and you're adding it into your benzene group. That's it. Pretty simple. Pretty simple. It just takes practice. Okay, this one. Name of the reaction.
You got a U-shaped double ring.
I think I call
Mm,
It's alkylation, but.
It's
essentially
alkylation.
You're just adding the rings together. You're getting
So,
a
yeah.
U-shaped double ring.
Okay, so that's what happens in the very first step. We get a primary.
it. Yeah, I understand.
We do a little hydrate shift. Let's just write it here. And that's how we get the carbocation in the secondary position. And it's also benzylic, so it's really stable. And now we have our initial benzene group, and we're just connecting that carbocation. And that's it. It's not bad. Thank you. It's not bad. As long as we memorize the rules, we should be good for this chapter. So far, questions in any of the reactions that we just went through? Okay, we're processing it. That's okay.
The bromine leaves when we're adding that second ring, correct?
Yes.
Great.
For alkylation and acylation, you always have some sort of leaving group, which is just a halogen. So that method group is this one right here. Let's label this actually, so we can keep track of everything. Okay, we're all good?
Another one.
Okay, actually, let's go to a conceptual question this time. Which one is going to be able to undergo any Friedel-Crafts reaction? So that means acylations or alkylations.
Wait, no, that's, no, that's the intermediate. So
Apologies.
Wait, but can't we just? Oh no, 'cause the whole point is that you need the carbocation on the other ring, so you can't skip that stuff. Okay. Well, let's see.
Okay, let's just quickly review the rules of real cross reactions. What were the main rules?
So it's an activator.
Those are not the rules of the
Oh,
reactions.
The activator,
No reaction if you have any strong deactivators or amines. Okay, so
these are.
let's just start looking at them. That's why that chart that I gave you initially, that's why you have to memorize that one. That's the one that's going to be really the key for this chapter. So in this case, let's just go molecule by molecule. Molecule A. In this case, we see, oops, that's too loud. That's NO2. NO2, is it a withdrawing or donating group?
The withdrawn group.
It's a withdrawing group, which means that it's a deactivator. More specifically, it's going to be a strong one because remember, the only weak deactivators, they're just your halogens.
So regarding the strong deactivators versus like the regular deactivators, are
Everything
these-
that's
are
red.
these three, like right here?
Those are the strongest, yes, but anything that's
So
red,
this isn't considered a strong deactivator?
anything that's red, it's going to be a strong deactivator. But the ones that go more to the right, those are even like the strongest of all. Okay, so we have a strong deactivator, so that means that A is not going to happen for that reason. Now in B, I have an acyl group connected first. Is that an electron withdrawing or donating?
Withdrawn.
It's a withdrawing group, so that means that it's a deactivator. And since it's not a halogen, it's a strong deactivator. So again, B is not going to happen. Option C,
That's
This-
the activator.
it's a deactivator, same process. So C can work. What about option D? In this case, it's different, exactly. We have that carbonyl, but the oxygen with the lone pairs is connected first. So that means that the electron donating effect is going to come first before the withdrawing. So this guy is your activator, so D is going to able to undergo Friedel cross reactions. Molecule E, what kind of director is this? It's cyanide, yes, but is it an activator or deactivator?
Yeah, strong deactivator.
It's a deactivator, it's a strong one. So E doesn't work for that reason. F,
It's a-
bromine,
It's a withdrawn group.
Yeah.
strong withdrawing groups or strong deactivators, they mean the same thing. Bromine, what's that?
Withdrawn.
Yeah.
It's withdrawing, but it's a weak one. It's a weak deactivator. So technically, this guy can undergo Friedel cross reactions as well. So we have practically two answer choices, but which one is going to be the best one? D or F?
D.
It's going to be D. Exactly. You're going to prefer to have an activator over a deactivator, even if it's weak.
And only because it's an ether before the carbonyl.
Yes.
So basically, so yeah, this makes memorization stuff. Memorize this one's like activator.
So yeah, as long as you memorize that chart, the blue, the green, the red, you should be good.
Options and the carbonyl was closer to benzene than the pure would that one be better? Does that make sense? Like,
So notice how B and D are practically the same thing. They're just flipped. One of them has the carbonyl connected first because that carbonyl is directly connected. It's withdrawing, so it's not going to happen. But if the other portion, the one with lone pairs, comes first, then it is going to happen.
I think it's the sense that the carbonyl is working through inductance in D.
Yes.
Versus,
The lone pairs, they work through resonance.
resonance.
So yeah. And actually, on Monday, we're going to be talking about resonance. We're going to do a quick review. So don't get too scared. So yeah, it's going to be this one right here. And actually, you guys can give it a try on your own. Just give it a try on your own. And after that, you're going to see why specifically activators go to ortho and para and why deactivators go to meta positions. Okay, everything is explained by resonance.
We're gonna do this together, right? Or-
Yes, we're going to do it together. But if you can, do it on your own. Give it a try on your own. Okay, guys, so I'll see you Monday. So again, just relax for the weekend. You guys did great on the exam. It's okay. Just relax. No problem.